Yeah, still good morning for everybody. That's my pleasure to thank the organizers for this wonderful invitation. And I'm happy to talk to this large audience of different background. Let me begin with my curiosity. Can you hear me? Of course. Is it loud enough?
I can make it a bit louder, I think.
Even louder.
Okay, now.
So if you don't mind, I begin with my curiosity of the ratio of colleagues in the audience who never before heard about the concept of spontaneous collapse. Don't worry to make a sign like this. Okay, I have no impression of the number, the ratio. So at least
wave function collapse before, about the wave function collapse models. Who did it? Who did it?
Okay, so it's about one-fifth of the audience, or a bit more. Well, what I'm trying to do is to deliver a simplest possible introduction to the so-called spontaneous collapse theories, models, based on your textbook knowledge of quantum mechanics and particularly of standard quantum measurement. Yes, this introduction is a bit contrary to the traditional introductions of the concept of spontaneous collapse. My own understanding has been changing over the 30, 40 years, and now my own understanding is that simple that you will see in a few minutes. Let me start with something which is absolutely standard. It is von Neumann's proposal, how you measure an observable, like X with the hat, operator X, which may be a spin, it may be a position. In our case, it is a position that is a continuous variable. The last page of von Neumann's book is about this mechanism of unsharp measurement of the observable X. The precision or the unsharpness of the measurement is sigma. And the measurement, like all typical measurements, is irreversible. It alters the energy and the momentum of the measured system. And the basic mechanism is the so-called collapse mechanism. Yes, and I call it, following the modern terminology of measurements, I call it selective measurement. And it is, as you see, a nonlinear and stochastic mechanism. Psi is the pre-measurement state vector. It is standard in conservative quantum mechanics that we need a measuring device. And if we apply the device, then we got post-measurement conditional state conditioned on the measurement outcome X without the hat, so it is a real number. And in case of von Neumann detector, this exponential factor will reshape the pre-measurement wave function. The outcome X is random, and the probability of it, the probability density of it, P of X, looks like this. It is, of course, a quadratic function of the state vector psi, the pre-measurement state vector. Now, this I call selective measurement because I select the post-measurement state according to the measurement outcome X. I call it collapse, and it is, remember, it is nonlinear and stochastic. The contrary or simplest mechanism is the non-selective measurement, which means that I have no access to the measurement outcome X, or simply I neglect it. Then the post-measurement state after the device is a mixture of the conditional states like this. And what is extremely important, then the mathematics is much simpler, much simpler than the mathematics of the selective measurement, which is nonlinear and stochastic. The mathematics of non-selective measurement is always deterministic and linear. If rho is the pre-measurement density matrix, then the post-measurement density matrix is just a linear, completely positive map of the pre-measurement density basis. So remember that the non-selective measurement, which results in decoherence instead of detailed collapse, this is much simpler in its mathematics than the collapse mechanism. But both of them are irreversible, lead to energy momentum non-conservation of the measured system. Remember those features, please. And more than 50 years after the von Neumann standard measurement, we constructed some generalization of it or some application of it, which is called quantum monitoring. And it is as standard as von Neumann measurement. Nothing new. You can derive it from standard quantum mechanics. And it happened in foundations by people like Nikolai Żyzan and myself, in mathematical physics by Slava Belavkin, in very, compared to my taste, he developed it in a complicated formalism, mathematical formalism, but it is, at least it is rigorous, absolutely rigorous, unlike say my derivation, which was completely heuristic. And the third context where this calculus was invented and derived was quantum optics by Weissman and Milburn. Now, quantum monitoring is time-continuous measurement. For instance, one way to construct the mathematics of time-continuous measurement, if we repeat the previously learned von Neumann unsharp measurement of sharpness, of unsharpness sigma many times at an infinite rate of repetition, and the unsharpness goes to infinity, and the rate goes to infinity too, while we keep the ratio gamma constant. And this limit is totally robust and gives you a reasonable, nice theory of quantum monitoring. This is one way to get it. And gamma is called the strength of monitoring. Now we can define selective monitoring, which is the dynamical version of collapse. And this is the resulting mathematical structure of the equation of the stochastic nonlinear Schrödinger equation, which governs the conditional state conditioned on the measurement outcome X, which is now called the signal, following the standard terminology of control, of classical control theory. And it is a time-dependent function, of course. And the conditional state evolves according to this tricky equation, where H is the self-Hamiltonian of the system under monitoring. This term is the nonlinear deterministic term. Look, there is no I in front of this term. So this is a non-Hermitian, nonlinear potential, so to say. And its role is to localize the wave function around the expectation value. And the price to get this localization is randomness, because don't forget, this is developed out of the stochastic collapse of a single shot measurement. So we need some randomness in it. And this last term is a random term where WT is a standard Wiener process. Let me mention that this stochastic equation should be understood in the formalism of Ito. So this is just a phenomenological, pedagogical version of the Ito equation. Now, the random outcome will interpret the noise in a second, because the random outcome contains the time-dependent quantum expectation value in the conditional state at the moment t, and it has a noisy part. It's measurement. It's monitoring, so it must have some noise upon it, and this noise is just the noise that is driving this nonlinear Schrödinger equation, stochastic Schrödinger equation, over the square root of the strength of the monitoring. Let me waste some more minutes here. Look, if the strength of the monitoring gamma goes up, you get stringent information, stringent way to monitor the observable X, and then the noise goes down. So the higher the strength of the monitoring, you get a sharper value for the outcome. Now let's come to the non-selective notion of non-selective monitoring, which means that you don't care of the measurement outcome, the signal. You average over it. Then the mathematics becomes much more simpler, like in case in the one-shot von Neumann measurement, and you get a linear deterministic master equation for the density matrix, which is the stochastic average over the conditional states, like in case of the one-shot measurement. And here you are. This is the simple master equation, where this complicated, detailed collapse equation reduces to. And the second term, a double commutator in X, It might be new for some people in the audience. It is a non-Hamiltonian part in addition to the standard one. And its influence on the density matrix is a tendency to diagonalize it in the eigenbasis of the measured operator X with the hat. If there is no Hamiltonian, then the diagonalization will be saturated for exponential long time. Now we come to something new, which is not standard, but it goes closely after the standard concept of quantum measurement, standard measurement, and standard monitoring that I talked about in the previous slide. So spontaneous measurement and monitoring, why do we need it? Let me summarize what standard quantum measurements and monitorings are. They are the unique mechanism of classical data emergence from about a quantum system. There is no other way to get classical tangible data out of the state vector. This is very important. But on the other hand, standard quantum measurements and monitorings assume the presence of a measuring device, which is completely okay and confirmed in case of usual microscopic degrees of freedom. Over 100 years, we never detected any departure from the conservative traditional quantum measurement theory. But they are annoying in macrosystems. There's two ways to get rid of this conflict. Either we say that quantum mechanics does not apply but to microscopic degrees of freedom. Forget about quantum mechanics of the macro world. Now that was the view in the first few decades of quantum mechanics, but after then, in our era, we talk about quantum cosmology. So now we adopt the other view that quantum mechanics is universally valid in the micro world and in the macro world equally. Then we have to do something with this annoying necessity of measuring devices. Why exactly we are annoyed? Are we annoyed? That's the famous paper by Mermin and two quotations of the genius of previous generation compared to even to Mermin. Pascal Jordan, observations not only disturb what has to be measured, they produce it. We compel the electron to assume a definite position. We ourselves produce the results of measurements. This is the annoying traditional conservative standpoint. But Pais quotes Einstein himself. I recall that during one walk, Einstein suddenly stopped, turned to me and asked whether I really believed that the moon exists, meaning the position of the moon exists only when I look at it. So Einstein was annoyed by the standard standard views of in quantum about macroscopic quantum mechanics. Yes, no. Here I am. So that's why if quantum mechanics is universal, it's yeah. If it is universal, then to avoid this annoying necessity having measuring devices to get any classically tangible data out of a quantum system, we have to make some assumptions, and the simplest, straightforward, I mean, the best way, the easiest way to get rid of the devices and the traditional annoying way to get classicality out of the quantum, of we assume that there are spontaneous quantum measurements and monitorings, deviceless. They must be weak and negligible in microsystems. They would amplified and dominant, would be amplified and become dominant in the micro world. Still, they retain the mathematics of standard measurements and monitorings, which I introduced you to. So they may have the same mathematics, which is a great advantage. And they will explain the emergence of classicality in the macroscopic degrees of freedom at the following price: a tiny irreversibility and non-conservation of energy momentum. I recall that spontaneous measurements are measurements, deviceless measurements. They violate energy momentum conservation of the measured system and the reversibility of the evolution of the quantum state in the same way and for the same reasons as standard measurements and monitorings do. Now, I think that you might construct your spontaneous measurement theories. The point is what the measured observable would be, and then how you parameterize the equations that are the same equations as in standard quantum mechanics, same monitoring equations. And here you are, historically, we got three different, somehow related models: the GRW, the DP, which I share with Roger Penrose, and the CSL. And as you see, the GRW, in GRW, the monitor observables are the positions of the elementary constituents of the quantum matter in the universe. In DP and CSL, the measured observables consist of the local mass density operators, which I denote by mu of x. In proton, the measured observable is the mass configuration operator. And there are different parameters. What is important is that GRW and CSL have two phenomenological parameters related to each other. I mean, CSL parameters are inherited from the GRW2 parameters, while the DP has only one parameter, sigma, which is the spatial resolution of the monitoring, how you monitor the local mass densities. The other parameter is universal. It is the Newton constant over h bar. So I think this is a nicety of the DP over the other two models, but it doesn't make life easier or simpler if you vote for DP instead of CSL. Yes, that's the Girard-Rimini-Weber Bell model. Bell gave the ultimate form of the theory. And I don't think I have enough time to interpret this this model. It is a history. It is I think it is now considered a toy model. The primitive, the first systematic construction of a spontaneous collapse model, universal spontaneous collapse model. Let me jump to the continuous spontaneous localization model, which was built on the GRW. Actually, it is the continuous version of the GRW model, where instead of the particle positions x with the hat, the measured observable is the Gaussian smeared mass density distribution. Smearing G over there. Where is the red? Yeah, it's there. So this is a Gaussian of width sigma. So that guy on the left is the sigma smeared mass distribution, non-relativistic mass distribution of the quantized matter. Sigma is needed because if sigma is 0, and this is the delta function, then the CSL blows up, the DP model blows up. So we need at least one new phenomenological parameter to make our spontaneous collapse models tractable or somehow consistent. So this object is spontaneously monitored at effective rate, which is again a phenomenological parameter in the CSL theory. The selective monitoring equation looks like this. It is the same structure as you showed you for a single observable X. It is just a generalization for infinite many observables represented by the mass density mu with the hat. So this is the localizing term, which tends to shrink the mass configuration close to its expectation value. And here we have the obligatory stochastic term, where WT of X are independent standard standard white noises. The measure signal, which is a classical time-dependent mass density function, spatial mass density function, it is of the structure similar to what we learned about the standard monitoring. It is the quantum expectation value plus some noise, which is inverse proportional to the square root of the strength of monitoring. M0 is it sets the mass scale of the model. It is the atomic mass unit, another phenomenological parameter. Yes, And now look at the non-selective spontaneous monitoring equation, which doesn't give you the collapse, it gives you the dynamical decoherence, that is a diagonalization of the density matrix in the functions of mass configuration. So macroscopically different mass configurations will lose their superposition. They will lose their interference. You can confirm for yourself that the scales are perfect for electrons. This decoherence term, where it is for electrons, this term is ignorable because the mass of the electron is small. On the other hand, for massive degrees of freedom, you get localization. So if you have a cube of sugar or just a nano grain, you get fast diagonalization, say in the position of a sugar cube or of a nano grain. So it is a plausible theory that unifies quantum mechanics of the microworld, which is untouched and unaltered, with quantum theory in the macroscopy. And how many? Zero. Zero.
We want to have some time for discussion, then.
Yeah. So that's the gravity-related spontaneous collapse, where the strength of the monitoring is proportional to the Newton's constant. Forget about the nonlinear stochastic Schrödinger equation and come to the simplest equation, which doesn't give you collapse, it gives you dynamical decoherence, disappearance of interference terms between macroscopically different massive mass configurations. So that's the central equation of this model, which I share with Roger. We don't share this equation. It is mine. What we share is in here. We agreed, we start from the incompatibility between quantum theory and general relativity according to Roger, and Newtonian gravity in my analysis. And we come to the same non-relativistic measure of this ambiguity, which comes from the said incompatibility. This is what this is what we share. It's a non-relativistic measure of uncertainty, of incompatibility between quantum and gravity. And you say that Roger proposed no dynamical equations. He pays no price. That I do, because I have the collapse equation, the non-linear stochastic Schrödinger equation on the previous slide, and the simple master equation at the bottom of the previous slide. And the price I pay is energy momentum non-conservation and, of course, some irreversibility. And again, that we finally share with Roger is the decay rate of left-right superposition of a massive object. If M is a big mass and it is in superposition in left and right positions with a macroscopic distance, then according to Roger, myself, there is a decay rate of this superposition, and the decay rate looks like this, where this delta E gravitational is just the below combination of the of the standard classical Newtonian interaction potential between the left-right mass configurations 2 times minus the self Newtonian interaction of the left-left and similarly of the right-right mass configurations. That we share, and that's my summary. I'm afraid I have totally run out of time. You mean?
Yeah, more or less. But
More or less. So read the sentence. This is just a repetition of the previous one. Nature is extremely weak, but otherwise standard quantum measurements of particle positions or mass configurations everywhere and time in the universe. There are no measuring devices. The mathematics is the same as if there were measuring devices. And we got a unified theory of micro and macro world. This is a postulation. This is not a necessity that you go this way. But it deserves to have constructed this theory. And there are a lot of other things, contacts, which would be good to talk about, but I think I ran out of time.
well, thank you very much for the fascinating talk.